Yeah, so I'm presenting on joint work with Patty Commons, David Libbenowel, and Tina Liu. And I'll start with an introduction to these chain letter petitions that are in the title. Can everyone see the slides? Still good?
We can.
Okay, excellent.
Yes,
so these chain letter petitions are really the motivation for our work. This is the introduction from an email that circulated in 2003. It's a chain email protesting the Iraq War. So basically it says, we think the Iraq War is a bad idea. If you agree, then sign your name at the end of the list and send it to all of your friends. And then eventually send this email to the White House and the UN. This spread very widely. It generated about 3.5 million emails and gathered about 170,000 signatures total. And the interesting thing about these emails is how they spread. So if we take a look at the instructions, it says, please copy this email in a new message, sign at the end of the list, and send it to all the people you know. So let's say the first person who starts this petition is Alice. She sends it to her friends. Bob decides to sign his copy of the email. Bob sends it to his friends, Carl and Dan, who both signed their copies. So now at the end of this process, we have 2 active copies of the email. The first has the list of signatures, Alice, Bob, Carl, and the second, Alice, Bob, Dan. And when we observe these emails, we can either find them posted online, or the one I have a screenshot from here is from the George Bush Presidential Library. And when we observe those emails there, we only have access to those final list of signatures. We don't get to see the tree that represents how the email spread. So the question we focus on is, can we reconstruct this tree just from the signature lists that we observe? And in this small example, the answer is clearly yes. Since the 2 lists of signatures agree on Alice and Bob and then split on Carl and Dan, this tree here is the one that represents how the email spread. But in practice, the problem is much more difficult. And that's because copy pasting is a lot harder than it seems. So when people copy the email into a new message and sign their name at the end of the list, they often introduce mutations. We've observed substitutions where people will replace previous names with new ones, either accidentally or on purpose. We've seen insertions and deletions. There are also character level errors that show up. People will edit previous names. Maybe they're retyping them, thinking that they're correcting errors. And yeah, all of these errors are present in the Iraq War petition. So when we're reconstructing the tree, we need to be able to account for all of these. And when we have mutations, this reconstruction problem is much more difficult. So even in this very small example, it's unclear whether Carol is a different person from Carl, or if that's an edit of the same name. Is the Carl in the first list the same as the one in the third list? That would require that Bob was deleted. Those are the kinds of things that we think about. And this reconstruction problem is especially interesting because chain letters have these 3 key features that show up elsewhere in reconstruction problems, but that really seem to come together uniquely in this domain. The first one is that these chain letters grow at one end, so they accumulate signatures at the bottom. They diverge, so when I send an email to several people, each of those copies grows independently. And they mutate and inherit mutations. If I make a mistake in my copy, that mistake is inherited by all of the people that I send the email to. So I'll briefly summarize our contributions now. First of all, we've formally defined this reconstruction problem. There has been some work on chain letter reconstruction in the past, but it's used ad hoc methods. So we now have a formal objective. We have an NP hardness proof of this problem, an optimal solution when there are 2 lists to reconstruct. We also show that the problem is fixed parameter tractable. So if we have a constant number of lists, we have a polynomial time algorithm for this reconstruction problem. And for an arbitrary number of lists, we have a fast heuristic whose running time depends much better on the number of lists. Finally, we experimentally evaluate our algorithms on synthetic data, where we know what the true propagation tree is. For the NP hardness proof and the fixed parameter tractable proof, I would direct you to the paper. I'm cutting those out for time. So let me quickly go over some related work. There has been research done on chain letters in the past, especially on the structure of this Iraq War petition tree. There's also been some work on reconstructing this propagation tree from the plea, from that introduction at the beginning of the email, and looking at mutations that occur in the plea. There's also related work that shares two of those three key features, but that doesn't share the third. So, for example, if you have one-ended growth and divergence, but no mutation, then the optimal summary tree is a trie. And we've seen those in previous talks. And one area where this shows up is in online conversations. So if I have a conversation thread, people can split a thread into two subthreads and can add replies to the end, but there's no obvious sense in which previous messages mutate. You can also have divergence and mutation without one-ended growth. And this is where the very large field of molecular phylogenetics fits in, where you're reconstructing evolutionary histories from mutations in DNA sequences or proteins. But unlike chain letter petitions, DNA doesn't accumulate new material at one end. And then these divergence and mutation characteristics also show up in storytelling. So there's been work on reconstructing the history of Little Red Riding Hood from mutations that occur in different tellings. Okay, so I'll now talk about the actual reconstruction problem. So first, to give you some intuition about the problem, we call this the Diverging String Sequence Summarization Problem, or DSSSP. And the input to this problem is a collection of diverging string sequences. And what I mean by diverging is that every pair of these sequences has some approximately shared prefix. This may include mutations. So for example, these two lists, the approximately shared prefix could be Alice Carl and Alice Bob Carol, if we hypothesize some mutations. And then the idea is that in this collection of sequences, we can represent their shared history as a tree. And the goal of this problem is to find the best summary tree. Now, what exactly I mean by best will take me a little bit of time to get through. And that's because there are a few competing objectives. There are a couple of different things that we'd like this best summary tree to satisfy. First of all, we'd like it to accurately represent all of this input string sequences. And what I mean by that is that for every input sequence, there is a path in the tree whose labels match with the input sequence. And this tree here that I've shown matches the input sequences exactly. So Alice, Carl, Eve, Alice, Bob, Carol, Dan, and Alice, Bob, Carl, Frank are all exactly represented by label sequences in the tree. On the other hand, we also want a tree that's minimally redundant. We want to capture the shared prefix structure by avoiding repetition of nodes. So if we think that Carol is just a mutation of Carl, we actually want Carl, Carol, and Carl to all map to that same node in the tree. And as you can see, these two objectives are in conflict. So how exactly do we measure these things? Well, one thing you've noticed here is that in the minimally redundant tree, while I've minimized the number of nodes, now the sequences don't match up exactly with label sequences in the tree. So here, the first sequence has the insertion of Bob, the second one, the Carol node maps up to Carl, etc. So to address the first point, how do we measure representation accuracy? How well each sequence is captured by the tree? Well, first of all, we compare each sequence to its corresponding label sequence in the tree. So here we've introduced notation for the label sequence in the tree of each input sequence. And then we have an edit distance measure between each input sequence and its label sequence in the tree. This is very similar to standard edit distance. We call it asymmetric edit distance since we're disallowing deletions. I'll talk about why in just a minute. So in this asymmetric edit distance, when we're transforming X into Y, we can insert strings, we can substitute strings, and the costs of those edits are computed using Levenstein edit distance. So for example, when I'm transforming X1 into the label sequence of X1, I have to insert Bob, and that costs 3, one for each character. So then to minimize redundancy, notice that in this minimally redundant tree, we have 2 fewer nodes than in the accurate representation tree. So in order to encourage fewer nodes, we're going to impose a cost lambda for each node in the tree. And then going back to why we don't allow deletions when we're comparing sequences to their label sequences in the tree. If we did allow deletions, even if we just had a single input sequence, if the cost lambda was high, then we'd want a tree with no nodes. And to preserve the intuition that we should actually be representing that sequence, we require that each label sequence is at least as long as its input sequence. And this corresponds to disallowing deletions in asymmetric edit distance. So now, formally, the DSS-SP. We're given these collection of m diverging string sequences and a node cost lambda. We want to find the tree T that minimizes this error function. It has two components. The first is the sum of all of the asymmetric edit distances between the input sequences and their corresponding label sequences. And then the second component is cost lambda for each node in the tree. We think of this as a loss and regularization, since we're trying to minimize the loss, minimize the error with which things are represented. But this might cause overfitting, so we regularize the solutions by encouraging the trees to be small. Excellent. So how do we solve this problem? First of all, if we have two input sequences, we can actually optimally solve it using dynamic programming. So I'll quickly go over this dynamic programming recurrence. This looks very similar to standard edit distance with a few interesting additions. So here we have two input sequences, X and Y, and this EDG recurrence edit distance with give up is the cost of aligning the string X from index I to the end and the string Y, the sequence Y from index J to the end. It's the minimum over the allowable operations, just like in edit distance. I'll go over this first term. The next terms will look similar. So in the substitution operation, the first term is the recursive call. Then we incur a node cost lambda because we've added one node to the tree. And then we have this edit distance term, which corresponds to the alignment cost of aligning a string to that first node. So for this first node in the substitution case, we can label it by xi or yj, it doesn't really matter, or anything on the path of shortest edits from xi to yj. And let's say we label it by xi. Now we have to align yj to that node, so we have to pay the edit distance between xi and yj, and then the node cost for that node, and then the recursive cost for the subtree below it. The insertion and deletion cases are very similar and symmetric to each other. And then the last operation has to do with this diverging process. We call it the give up operation. So here you stop doing the complex alignment. You just decide that the two strings diverge below this point. And you pay all of the node costs for all of the nodes below the divergence point. So you're paying a large upfront cost to avoid paying all of the edit costs that you would have to pay otherwise. And something we prove in the paper is that if you run this dynamic programming algorithm, you get an optimal DSS-SP solution for two sequences. Great. Unfortunately, if you have more than two sequences, the problem is NP hard. We prove this in the paper with a reduction from shortest common supersequence. You can also prove it with median string. Take a look at the paper for details. So how do we solve it, given that it's NP hard? Well, we have an idea for a heuristic based on progressive alignment, which is a multiple sequence alignment heuristic. So the way this works is that you repeatedly merge the pair of sequences that are most similar. And in the case of these diverging sequences, you want to be merging pairs that diverge last. So if you imagine a large collection of strings, you're repeatedly kind of stitching together these strings from the bottom up so that you build the tree in that way. So let's take a look at what this looks like. So we have these three input sequences. We first compute all of the pairwise alignments using this EDG dynamic programming algorithm. And then we identify the pair that has the longest shared prefix. So in this case, that's the pair x2, x3. We're going to merge those and consider their merged prefix to be a new sequence. So we merge the prefixes according to our alignment, and now we only have two sequences remaining, the combination sequence x2, x3, and the sequence x1. Again, we then compute all of the EDG alignments, and the alignments that we've computed thus far allow us to stitch together the tree. I'm omitting a couple of details here. I'll talk about those, some of those details now. So first of all, how do we label the final tree? So when we're repeatedly merging sequences, we're combining these labels into lists. So we really end up with a tree that's labeled by lists of strings rather than by individual strings. And to pick which strings to put in each node, we use the medoid string. This is the string in the list whose edit distance to the other strings is minimized. Ideally, we'd be using the string median here, since that is among all strings, what has minimal sum of edit distances to the set. But finding the median string is NP hard. So we're using the efficiently computable medoid instead. Another thing that we need to do to make this algorithm work is generalize this dynamic programming algorithm to handle sequences of lists of strings. Since once we've merged prefixes together, we now have a sequence of lists of strings that we'll need to run the program on again. And the way we do this is by defining a substitution cost for two lists of strings. Once we've done that, the rest of the algorithm is easy to define. So this substitution cost for two lists, we define as the error that we incur if we merge the two lists minus the error if we don't. And this is the error according to this asymmetric edit distance. So the idea here is that we're figuring out how much more alignment error we'll have to pay if we choose to do the substitution rather than if we don't. And then insertion and deletion costs are just substitutions with lists of empty strings. So the rest of the algorithm is straightforward. So some empirical results. In order to generate synthetic data to run these algorithms on, we first run a branching process just to generate a tree, which we label with random strings. And then we simulate this noisy chain letter propagation down the tree. So we simulate the process of Bob appending his signature to the petition and potentially introducing errors. The errors that we introduce can be either at the level of characters, like replacing the I in Alice with a Y, or deleting the second B in Bob, or they can be at the level of strings. So here, the name Bob was replaced with the name Eve in the first list of signatures. And then once we have this final collection of noisy signature lists, we run the reconstruction algorithm and evaluate how well it does. So in particular, we compare our algorithm, which we call build tree, to the ad hoc method that was used in the original Liebenau and Kleinberg paper, looking at the Iraq War petition. So here we're looking at 500 trials of a 15 sequence reconstruction. So each of these trials, we generate data independently. On the y-axis, we have the error metric that we defined, the sum of asymmetric edit distances plus the node costs. And then on the x-axis, we have the reconstruction parameters of the two algorithms. So for our algorithm, we have the node cost. We call the node cost in reconstruction alpha, since it can be different from the node cost in evaluation, which here is set at 10. And beta is the parameter of the Liebenau and Kleinberg algorithm. And we see that when we're evaluating with lambda equals 10, picking alpha anywhere between 5 and 20 gives very good performance, significantly better than the previous method. And these shaded regions are standard deviations. Another thing that we saw is that when we reconstruct more sequences, so this is 100 rather than 15, we get an even bigger performance gap. So now each of these subplots is looking at a different node cost used in evaluation from 5 to 20. And we see that across all of the evaluation node costs, we're performing significantly better across a range of reconstruction parameters. And we see this kind of flat-bottomed basin shape, which indicates that if we want an optimal solution for lambda equals 10, we can pretty much pick lambda anywhere from 5 to 20, and we'll get very good solutions. Finally, we also compare the reconstructed trees with the true propagation tree that we know since this is synthetic data. To do that, we compare the trees using tree edit distance from Zhang and Shasha. And here, the Liebenau and Kleinberg method performs better, although we are competitive at alpha equals 20. And the reason, I think, why we don't perform quite as well is that our algorithm is really designed to optimize this error metric and not tree edit distance. And we do perform significantly better under this error metric. So let me quickly go over takeaways from this talk. The first is that this chain letter reconstruction problem is really an interesting problem in and of itself, since these chain letters have these three key features: one-ended growth, divergence, and mutation, that are familiar in other contexts, but that kind of appear together seemingly almost uniquely in this instance. The reconstruction problem is NP-hard in general, but we have a dynamic programming solution for 2 sequences and a polynomial time algorithm for any constant number of sequences. And finally, if you have more than a constant number of sequences, we have an efficient heuristic that runs much faster in practice. A few open questions that we've been thinking about. So one of them is, it would be nice to have a formal approximation algorithm. Ours is just a heuristic. In particular, bounding the error that comes up from finding the wrong tree topology seems very difficult. The error from picking bad labels, picking the mutoids instead of the medians, is just a constant factor, but the error from topological mistakes seems much more difficult to bound. Another thing that would be interesting are algorithms for small node costs, lambda. If lambda is 0, if new nodes are free, then you can just build the trie representation of the input sequences. And that's the optimal DSSSP solution. Even if lambda is positive but very small, if it's small enough that even a single error is too expensive, then the optimal solution is still a trie. So an interesting question would be, how big can lambda get before the problem becomes really difficult? If lambda is small enough that we can only afford a bounded number of errors, is there an efficient solution? So I'd like to thank all the people on this slide. The paper and data and source code are all available online, and I'm happy to take any questions. Thank you.